Hello, my name is Abhishek Kade and today we'll be talking about collocated approach and staggered approach in CFD. So these are two different ways of solving a CFD problem, two different arrangements I can say, and let's see how it works. So starting with the Navier-Stokes equation. So a Navier-Stokes equation is first in an integral form. Then we discretize it so that we can solve it for our complex geometry. So after discretizing it, what do you think? What do we need to solve the Navier-Stokes equation? Yes, simply it's the points in the field, the node points in the field. It can be anything based on a selection. You can take any imaginary points in your field. But then what points do we need to select? What can be the different arrangements? Yeah, it sounds like low-key. So different variants are available, different arrangements, configurations are possible. And that's what we are going to see right now. So the first one is collocated approach. Collocated approach means something, we are arranging something or placing something in the same location. Same location. So that was quite important. So this was not used before 1980. Obviously, it had some reasons. So what it means is like the collocated approach means is that there is a red point here. These are the stencil, the cells. So we have a north cell, we have a south cell, we have a west cell, and we have an east cell. So north, south, west, east, and other direction. So I'm just showing a 2D picture instead of 3D so that you can understand. Now, what you can see is a red point that shows the cell center. Now, pressure, velocity, temperature, everything, velocity in x direction as well as the y direction, all of this are defined at the cell centers. But then what problem happens because of this while solving a problem? There are pressure oscillations. So actually, when you're calculating a mass source, now what is a mass source? If I say in simple terms, del Vx upon del x plus del Vy upon del y, the continuity form. Okay, so that is the mass source for each cell. For this, we require the velocities at the cell faces rather than cell centers, which is not possible here because we do not have, we need some interpolation so that we get at the cell faces, the velocity. So there are pressure velocity coupling difficulties, but more interpolations are required. But then, why it is popular today? Why this still this method is also popular today? It has so many problems because if you see right now, it's an orthogonal mesh. Okay, when it's a non-orthogonal mesh, when there are a lot of curves and the geometry are complex, would this face be like this straight? No, the face won't be like this. The face will be curved, tilted, everything, whatever you can imagine about. So for complex geometries, if you are defining the velocities on the face, imagine the faces are at different angles and you are using those vectors, velocity vectors at different faces. That's so complex, right? In that case, the collocated approach at a single point inside a cell would be so much easy. So same point for everything, that is very easy for the solver, and we can easily apply multi-grid solver procedures here. Now next, multi-grid solver procedures, yeah, what it is, the algorithms which we refine the mesh, increasingly coarsen the meshes, then refine it, all those things, the VW multi-grid algorithms. Again, that is a complete different story. Maybe sometime we can see later. Again, the Navier-Stokes equation, the discretization of Navier-Stokes equation is also a different story, which I just told you at the beginning. So that needs a complete different lecture. Next comes the staggered approach. So what is a staggered approach? Arranging in a series of alternating way. So let's see how it is arranged. So alternating way means something is defined at cell center and something is defined at cell faces. Now this is going to solve our problem. We had a big problem in the collocated approach, like the velocities were not defined at the cell face, rather than they were defined at the cell center. But here in the staggered approach, the velocities are now defined at the cell faces, so that we don't require any more interpolation. You can directly use the pressure in the momentum equation. The velocities are naturally defined at the locations where they should have been. So naturally aligning with the pressure gradients, right? So this is there. And the diffusion term, the derivatives that come inside it, these also do not require anything, because it is at the cell phases. So uh, in the collocated, obviously we had to do interpolation. Here there is no need of interpolation. You can use the second order accurate schemes or anything to solve in a staggered grid. What is a partially staggered grid? Okay, at some points the velocities and pressure are defined at the cell center itself and not like this in a staggered approach. So that is called as the partially staggered grids. So staggered and partially staggered, these are the two forms. Okay, so partially staggered may be for the complex geometries where somewhere we do not want to use completely staggered. Instead, we will use a combination of collocated and staggered, and that's how we'll make things powerful. So all this is about the different configurations. If you like this video, please subscribe the YouTube channel and connect with me on LinkedIn. And thank you.